Gnanam Paramam Dheyam. Knowledge is supreme.
Right. Last lecture we saw algebraic closure of a field exist and they are unique up to k isomorphisms. Now we come to the proof of fundamental theorem of algebra. So we are going to prove the theorem. This is also called FTA, fundamental theorem of algebra. Also, if you see the books, it is listed as D'Alembert Gauss. In French books, it is written as theorem of D'Alembert. In a German books, it is written as theorem of Gauss, and in English books, it is written as theorem of D'Alembert Gauss. So the field C. The field C of complex numbers is algebraically closed. So we will prove that every non-constant polynomial f with complex coefficients has a 0 in C. This is equivalent to checking C is algebraically closed. Every non-constant degree is bigger or equal to 1, it has a complex 0. This is what we need to prove. Proof. What will be used in the proof? That is first I will indicate. So, first of all, note that the definition of C is not completely algebraic. So, we have seen rational numbers and then real numbers and then complex numbers. This is contained here, this is contained here, and there is a big gap here. This gap is big and this is small. This is degree 2 extension. This is in fact C is R polynomial x modulo this prime polynomial x square plus 1, and this polynomial doesn't have real zeros. This is irreducible because R has order. So, no square will be negative. Therefore, this polynomial is prime over R. Therefore, it generates a prime ideal. Then this is a field, and that field is precisely C. This was what Cauchy's. And here we need limits. So, definitely we will have to use some kind of algebra, some kind of calculus, and this proof will contain least of calculus and more of an algebra. That is what it is planned. Okay, this is one remark, and the first observation, want to do that. This is easy. It is easy to check that if I have every polynomial of odd degree, odd is very important, odd degree G in Rx with real coefficients has a 0 in R. This is very easy. What you do is try to plot the graph of this function g. So observe that when you take x large positive, then obviously the sign of the gx will be positive. So I am assuming that we without loss we assume that leading coefficient of g is 1. If necessary we divide by that, because we only have to say something about 0. So because of that, the g of x, the value g of x will dominated by the leading term of the polynomial, so which is x power n. So when x is large positive, this will be positive. Similarly, when x is large negative, then the polynomial, the value of the polynomial at x will be negative. So therefore the nature of the graph of g will be like this. So therefore it has to cross x axis at least once, maybe several times, but at least once. So therefore now use intermediate value theorem. So that it crosses the x axis, so that means it has at least one real 0. So this was observation 1. The another observation we use is the following. This is observation 2. Every complex number z in C is a square of some complex number W. So that is, there exists W in C such that W square equal to Z. This is what we will also use in the proof later. You have given Z complex number is given. So look at the polar representation of this f. That means what? This is Z is somewhere here, and this radius and this angle. So this says Z, we can write it as, this is R e power I theta, where theta is in between 0 and 2 pi. Actually you can make it more precise, but it's okay. 0 is in between this, and R is a positive real number. So this R is in fact, if Z you have written it as x plus iy, then R is nothing but square root of x square plus y square. This is mod of Z. And theta is the angle that it makes it. So once you have Z like this, then you have a positive real number. Positive real number has a square root in real numbers. So therefore I can talk about square root of R, which is again a real number, since R is positive, this exists. And then this, so therefore I can take W equal to square root R times e power I theta by 2. Take the half angle. So this is clearly, when I square it, this will be R, and this will be by De Morey or by, so this is e power I theta, which is Z. So every complex number has a square root in complex numbers, that I am going to use, and every odd degree polynomial has a real 0 of real with real coefficients. All right. So also I will use Kronecker theorem. Which says that if I have a polynomial over arbitrary field non-constant, then I can enlarge the field so that all zeros are lying in that field. So this I will not state again. So this is what I will use it. Now let us start a proof. So proof of FTA. So let f be a polynomial with complex coefficients, degree f is bigger or equal to 1. This is given to us. Okay, the first of all, let us denote f bar to be the polynomial which I obtained from f by applying conjugate. So there is a complex coefficient, so I will apply conjugates to the coefficient. So this is a naught bar plus a1 bar x plus an bar x power n. So where f was a0 plus a1x plus an x power n. So this bar means complex conjugation. Okay. So this is another polynomial in Cx. And it's clear that f equal to f bar if and only if this polynomial has the real coefficients. That is precisely because we know that x is a real number if and only if x bar equal to x. Alright, so now we want to show that this f has a complex 0. So replace f by f times f bar. Now look at f times f bar is a new polynomial. This is also polynomial in Cx. But the advantage is this is actually real polynomial because when I take the bar of that, we will get so f by f. We are replacing f by f times f bar. The advantage is this polynomial f times f bar has actually real coefficients. Because how do I check some polynomial has real coefficient? I take the bar of that. Bar of that is ring homomorphism, so it is f bar times f bar of bar, but this is f bar f, which is the same polynomial. It's commutative, so it is f times f bar. So therefore it has a real coefficients. And if I prove that this polynomial has a complex 0, so if z in C is a 0 of this product polynomial, but this is same thing as f of z times f bar of z. And if this is 0, then this one of them is 0 at least. F of z is 0 or f bar of z is 0. If f of z is 0, we are happy. That's what we wanted. If this is 0, then you take the bar of that. So fz, f bar of z and bar of that is also 0, but bar of that is same thing as f bar bar of z, z bar. This is 0. But f bar of this f double bar is f. So this is equal to f of z bar, which is 0. So either this or f of z bar is 0. In either case, we have found a complex 0. So therefore, without loss, I will assume the polynomial has a real coefficient. So we may assume therefore f is actually a polynomial in Rx, and we are looking for f has a 0 in complex numbers, and we see it may not have 0 in R. That our typical example is x square plus 1, or for that matter any positive number, any positive real number a. Now we can talk about positive, negative and so on. So this, for example, x square plus a, that cannot have 0 in real numbers, because if it has a 0, then if it is b, b square will be equal to minus a. Minus a is negative, but b square is always positive. So therefore we cannot hope to find a 0 always in real numbers. Alright, so we may assume f is real numbers, f has real coefficients. Now look at the degree of f. Degree of f, we know it is bigger or equal to 1, it is non-constant. So I can always write in the form, this is d, which I can always write in the form 2 power n times q, where q is odd. Q is odd and n is a natural number. Maybe n may not, n may be 0 also. And I am going to prove the assertion, proof by induction on n. This is what I will prove. What is the assertion? By induction I will prove that this f has a complex 0, this n, and q is odd means 2 doesn't divide q. This is the setup. Okay. So induction will always start at n equal to 0. N equal to 0, what is the degree of f? Degree of f, n is 0, so degree of f is q, which is odd. Therefore, what I explained in the beginning, therefore f has a, actually in this case f has a real 0. By again I will say intermediate value theorem. So if you see in the history, intermediate value theorem was proved by Bolzano. This was proved by Italian mathematician Bolzano, and he didn't call intermediate value theorem, he called the zero theorem. So he called, he also stated in this language that it has a real 0. Alright, so therefore our induction starts. So our strategy will be now to, from a given f which has a real coefficients, construct a new polynomial which has a real coefficients, and this exponent of 2 drops, and therefore we can apply induction hypothesis to assume that the new constructed polynomial has a 0, and from that 0 we have to go back to the given polynomial. That is the strategy. Alright. So what am I going to do? So first of all, we know by Kronecker theorem says that I can enlarge my field of real numbers. There exists a finite field extension L over K or L over C such that f I can write splits in Lx. This I am writing in Lx. This is, I will assume it is monic for simplicity. So it will be like x minus a1, x minus an. A, not this n, a d, because the polynomial has degree d, and a1 to ad, they are elements in L. Because the same polynomial, I will think polynomial with complex coefficients, though it has a real coefficient. So I can enlarge the field L so that it has all the zeros lying in that field. And I want to now prove that at least one of the 0 is complex numbers. So to prove I belong to C for some I, that is what we need to prove. This is what we need to prove. Alright, so all our calculation is done in this is done because all our calculation we are doing it in the field L, or all the polynomials we are writing in Lx. That is why we have chosen bigger field, so that all the equations etc. will write in L. Alright, now that is our aim, that we want to check that at least one of them will lie in C, and but you will see the proof, two of them will lie in C. That is because this has a real, we are assuming this has actually real coefficients, and we know therefore if you have a complex 0, 1 0, then the conjugate of that is also 0. So, you will get two zeros, that is not surprising. So, that will also come out in the proof. Alright. So, what am I going to do with this now? I am going to, for a fixed real number, C in R, and any pair 1 less equal to I strictly less than J less equal to D. For this I am defining Bij's. These are the another numbers, all these are happening in L. This is by definition AI plus AJ minus or plus C times AIAJ. This is Bij. Strictly speaking, I should write the notation Bij, and this Bij depends on this C, therefore I will write Bijc. But I will use this only when it is necessary. It will come at some stage where I have to use this, that it depends on C. But right now C is fixed and I am considering these Bij's. And with this Bij I am considering a new polynomial. Or remember, our problem is to construct a new polynomial whose degree, in the degree the power of 2 drops. So, we are considering now a new polynomial. Consider a polynomial nu gx. This is by definition product is running over 1 less equal to I less than j less equal to d x minus bij. Look at this polynomial. So, where is this polynomial? This polynomial is a priori in Lx, because Aij's are in L, and therefore and R is in L, therefore C is in L, and therefore all these coefficient, all these this product is in L. So, it actually splits in L, and these are the roots. What are the degree? So, let us find out what is the degree of G. Degree of G is the number of pairs with this property. So, this is cardinality of the set of all pairs I comma j such that 1 less equal to I less than j less equal to d. This cardinality is precisely, you know it is d choose 2, which is half d into d minus 1, which is half d. I know d we have written as 2 power n q times this d minus 1. And remember, we are assuming now what? We are assuming n is at least 1, and therefore d is, what is d? D is 2 power n q. Q is odd. Therefore d is even, because n is at least 1. D is even. So, d minus 1 is odd. So, this is odd, therefore this is odd. And this is power of 2 is now 2 power n minus 1 times some odd integer. So, the degree of G has, in the power of 2 has dropped there. So, therefore, I will be eligible to use the induction hypothesis. provided I have to assure that this polynomial has a real coefficients. That is what we are right now. I only know this polynomial has only the coefficients in the field L, but now I want to check that this polynomial has coefficients all in real numbers. All right, so we want to check that Gx indeed a polynomial in Rx, so that we can apply induction hypothesis. So why that? Now look at the coefficients of G. Coefficients of G are. So what are the coefficients? So look here, I have the G and the coefficients when I multiply it out. They are elementary symmetric functions in Bij, are elementary symmetric functions in Bij. And what was Bij? Bij was Ai plus Aj plus C Ai Aj. And therefore they are so that implies coefficients of G are symmetric functions symmetric polynomials, I should say, symmetric functions in A1 to AD. That's also clear, because when I permute these Aij's, these Bij's will go to some BKL. So therefore they are symmetric functions in A1 to AD. I cannot say they are elementary symmetric functions in A1 to AD, but they are certainly symmetric functions, because these are elementary symmetric functions, and those when I permute AI's, they will not change. So they are symmetric functions in A1 to AD. Therefore our fundamental theorem on symmetric polynomial says that these symmetric polynomials are polynomials in, so the coefficients of G are polynomials in elementary symmetric elementary symmetric functions in A1 to AD. But what are the elementary symmetric functions in A1 to AD? So therefore coefficients of G, and where are the coefficients? With coefficients in R, because our base field is R. So coefficients of G are polynomials in elementary symmetric functions in A1 to AD. They are the coefficients of the given polynomial f. So coefficients of G are polynomials in the coefficients of f with real coefficients. So altogether that proves that coefficients of G belong to R. So we have proved that this polynomial G is actually polynomial has real coefficients, and we have used here Nice theorem, which is fundamental theorem on symmetric polynomials. Alright, so we have established the fact that coefficients of G are in R. So these G belong to Rx. We have already noted that degree of G is 2 power n minus 1 times some odd number. So therefore by induction hypothesis, one of the 0 of G should lie in complex numbers. So, there exists a pair I comma j with 1 less equal to I less than j less equal to d, such that this Bij, which is Ai plus Aj plus Caij, Aiaj, this should belong to complex number. This is by induction hypothesis, because I have a polynomial with real coefficients, a power of 2 has dropped, therefore the so this is, but this was happening for every C real numbers. So strictly speaking, I should write now C. So let me write that. That is very important now. So I am rewriting this. Rewrite. What did you get? For every C, a real number, I found a pair. The pair will also depend on C. I comma C, j comma C, such that 1 less equal to I comma C less than j comma C less equal to d, and Bijc, which is AIC plus BJC, not B, AJC plus C times AIC AJC. These belong to complex numbers for every C. But no, note that means what? We have defined a map. So that is, we have defined a map from R to the pairs with this property. No, we have defined a map from R to I comma j such that 1 less equal to I strictly less than j less equal to d, these pairs. This is a finite set of cardinality d choose 2, and we have a map, namely C going to ICJC. So we have a map. This, we know real numbers is infinite set, and this set is finite. So this map cannot be injective. Therefore, there are two non-equal real numbers, so that they have the same pair. Same pair means what? That means Bijc and Bijc prime, they are equal. But what is this equality means? This equality means what? This equality means, so the pair is, they are going to same pair. C and C prime go to the same pair. That pair I am calling it I comma j. So this C goes to this and C prime also goes to that. That means what? That means what is Bijc? This is Ai plus Aj plus C times Aiaj on one hand, and this is also equal to Bijc prime. That means this is equal to Ai plus Aj plus C prime times Aiaj, and C is not equal to C prime. Now subtract these equations. If you subtract it, this will go away. So when subtract, we will get this Ai will disappear, Aj will disappear, and C minus C prime will be Aij, Aiaj. So this C and C prime is in real numbers. So this is I know this is a real, these are same, and we know they are complex numbers. So the subtraction will also be complex number, because we are assuming this by induction, this has a complex 0 and the same thing as this. So this is in complex number, this is real number, and this is non-zero. Therefore I can conclude the product Ai Aj belong to complex numbers. When these belong to the complex numbers, C is a real number, therefore I can conclude immediately Ai plus Aj is also complex number. So I got a pair. So what did we conclude? The conclusion is there exists a pair I comma j with 1 less equal to I less than j less equal to d, such that AI plus AJ and AI AJ, both these are complex numbers. And from here I want to conclude now both individually they are complex numbers. That is because now look at the quadratic equation, x square minus AI plus AJ x plus AIAJ. This is a polynomial with complex coefficients and degree is 2, and we know how to solve this. The roots are, zeros are precisely what? Zeros are precisely our formula, that is minus b. So what are the zeros? They are precisely AI and AJ. And we know how to solve quadratic equations over C. That was just amount to say that if you can solve, so the zeros, our formula is minus the coefficient of b, that is AI plus AJ plus minus square root of b square, that is AI plus AJ whole square minus 4, this is AIAJ. But I know this is a complex number, this is a complex number, this is a complex number, so this is inside is a complex number, and square root is also complex number, because we have checked that for every complex number there is a square root is also complex number. So this is complex number, this is also complex number, so this is a complex number. So therefore, but they are actually this, the zeros are, when you simplify this formula, zeros are precisely this. The zeros are AI and AJ, so this is AI or AJ. So therefore they are complex numbers, and therefore we are done, because we have actually checked that 2 of them are complex numbers. Not surprising, because we had reduced to the case where the polynomial has real coefficients. So with this, now we have proved that fundamental theorem of algebra, which was very important, and as you see this proof has used the analysis least possible. Obviously, you cannot all the way avoid completely analysis, but this avoids many other. This is much, in my opinion, this proof is much simpler than any other proof, and let me say that this proof is actually based on the ideas of Lagrange. So with this, I will stop this, and we will continue our study of zeros of the polynomials on one side, on the other side the groups, and especially Galois groups of the field extension. So given polynomials we will construct fields, and given fields we will talk about groups, and then this interplay we will make it more and more intimater. That is the whole goal of this course. Okay, thank you.